We will now discuss the solution of a problem from the section Partial Differential Equations. This question is on the Lagrange's method of solving the first order linear partial differential equations. This question has appeared in the CSIR National Eligibility Test held on 16th February 2022, and it is from the section C. The given question is, which of the following expressions for u is equal to u of x comma t are solutions of u t minus e power minus t u suffix x plus u is equal to 0 with u at x comma 0 is equal to x. We are given four options. Option 1, e power t into x plus e power t minus 1. Option 2, e power minus t into x minus e power minus t plus 1. Option 3, x minus e power minus t plus 1. Option 4, x e power t. We are given a partial differential equation, that is del u by del t minus e power minus t into del u by del x plus u is equal to 0 with the boundary condition u at x comma 0 is equal to x. Then required to find which of the following four expressions are the solutions of this differential equation along with this boundary condition. We now discuss the solution of the problem in detail. We have u, a function of two variables x comma t, and given a partial differential equation del u by del t minus e power minus t into del u by del x plus u is equal to 0. Let's call this as the equation capital 1 with the boundary condition u at x comma 0 is equal to x. And what is this equation? The equation capital 1 will imply, we will write it as minus e power minus t into ux plus ut is equal to minus u. And how this is looking like? This is looking like capital P plus capital Q is equal to capital R. So it is a first order linear partial differential equation of the form P del u by del x plus Q del u by del t is equal to R, where P, Q, R are functions of x and t, where P is equal to minus e power minus t, yes, Q is equal to 1, yes, R is equal to minus u. Right. Now, we will solve this equation by Lagrange's method, and we write down the auxiliary equations. The Lagrange's auxiliary equations are dx by capital P is equal to dt by capital Q is equal to du by capital R. That implies dx by P is minus e power minus t is equal to dt by Q, that is 1, is equal to du by R, that is minus u. Now, to solve this, we will first consider the first two ratios and integrate. So now the first solution we are going to get dx by minus e power minus t is equal to dt by 1. It will imply dx plus e power minus t dt is equal to 0. The variables are separated. We are solving by by the separation of variables method. Now integrate. So the integral of dx plus integral of e power minus t dt is equal to c1, where c1 is an arbitrary constant. Integrating, we'll get x, and the integral of e power minus t is minus e power minus t is equal to c1. That is the first solution of these auxiliary equations. We'll try to get the another solution for this. So we take the second solution. dt by 1 is equal to du by minus u, and the variables are already separated here. This will imply du by u plus dt is equal to 0. Integrating, we'll get ln of u plus t is equal to ln of c2. That is, that will imply u into e power minus e power t u e power t is equal to c2, where c2 is an arbitrary constant. And the general solution is given by, c2 is equal to phi of c1. c2 is equal to phi of c1, and that is u e power t, u is a function of x comma t into e power t, c2 is equal to phi of c1 x minus e power minus t, where phi is an arbitrary function to be determined with the given boundary condition. We will do it in the next slide. That's what we have done so far. We will now take that condition given u at x comma 0 is equal to x. So put t is equal to 0 in the above, and u is equal to x you put. So that will be equal to uxt, t is equal to 0, ux0 is x, e power 0 is 1 into phi of x minus e power 0, that is minus 1. So that is x is equal to phi of x minus 1. That's the relationship, and that tells you what kind of function phi is. Now put z is equal to x minus 1. So this we put x minus 1. Then x will be z plus 1. Then x will be z plus 1. Then x means z plus 1 is equal to phi of x minus 1 means phi of z. So thus we get phi of z is equal to z plus 1. So the behavior of the function we have found. Now we will go back and get the solution. So the particular solution is u into e power t is equal to phi of x minus e power minus t, and phi is determined, phi of z is equal to z plus 1. So phi of x minus e power minus t is equal to x minus e power minus t plus 1. So now send this e power t to the other side. Then you will get u is equal to e power minus t whole into x minus e power minus t plus 1. Let's look at our options. Our answer, this is a solution. This is the solution of the given differential equation, given partial differential equation. And this is e power minus t, u is equal to e power minus t into x minus e power minus t plus 1. This appears against option 2. That means the solution what we have derived or got is appearing in the list of options against option 2. But this is a question given from the section C, so there can be more than one answer. So the option 2 is a solution, correct? That much you can say. So the option 1, option 3, option 4, are they solutions? How do we find it? And by this method we got one solution. Now what we can do is take 1, 3, 4 and by direct computation, that means u is equal to these things you take and partially differentiate with respect to t, partially with respect to x, and substitute in the given partial differential equation. Is it satisfying? So by direct verification, that means by directly taking this, the expressions given in 1, 3, 4 are not solutions of 1. This is left to you. So you take them and you calculate partially differentiate with respect to t, partially with respect to u, differentiate with respect to u, and substitute in the differential equation, and 1, 3, 4 are not satisfied. Therefore, they are not solutions of 1. Therefore, this is the only solution. Therefore, our answer to this question is option 2. And we will make a remark, by the by. You need not do this the entire process of executing that Lagrange's method of solving differential equation, partial differential equations. You need not. Anyway, you are verifying, direct verification you are doing. You do it for 2 also. For 2 also, by direct verification you do. Then this will be satisfying this one. So, without doing all this also, many of the students will do direct verifications they do, and they find 2 is the only solution. So, remark, by direct verification, the expression given in option 2 is a solution of 1 because that satisfies the given differential equation, and the expressions given in options 1, 3, 4 are not solutions of 1 because they are not satisfying the given partial differential equation. So, you can also do that. So, many students do it just by verification of these things without going into the method. But anyway, the method I have shown you, that is the best way of doing a question. Agreed. So, the answer to this question is option 2. That is the detailed discussion of the solution of the problem from the section partial differential equations, and the question is based on the Lagrange's method of solving first order linear partial differential equations. And I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.